Right, 2.4 by conditional statements. You can see that we did skip 2.3, and we are just skipping that in interest of distance learning, to be honest. It takes 2.2, it kind of puts it all together, and it makes it very confusing. And it's confusing enough teaching it in the classroom with all the students here, but it would just be way too confusing to teach a lesson like that through distance methods and whatnot. So we're just skipping it. We're moving on to 2.4. 2.4 does use 2.2, so make sure you go back and review your conditional, your converse, your inverse, and your contrapositive. But most importantly, those conditional and converses are what we're going to use today. So just a little bit to review. We know that a conditional statement is in the form of P implies Q. So if P, then Q. A converse statement is in the form of Q implies P. An inverse not P implies not Q. So a reminder that the converse is when we swap them. We swap our hypothesis and conclusion, and the inverse is when we negate them. So we use the word not. And then we have the contrapositive, which is going to be not Q implies not P. So it puts them both together. So it swaps it and it negates it. So using that knowledge, we're going to take this statement. So a cat is happy if and only if it is purring. We're going to write a conditional and a converse based on those two. So my first sentence is going to be if a cat is happy, then it is purring. So we can write that out. All right, so there's our hypothesis. If a cat is happy, and there's our conclusion, it is purring. So our conditional statement for this would be if a cat is happy, then it is purring. So the converse, remember, is just going to swap our blue and our red, or swap our hypothesis and conclusion. So go ahead, pause the video, and you'll see the converse. All right, so my converse becomes if a cat is purring, then the cat is happy. So once again, you'll notice we just switched the red and the blue. So we move the cat is purring part up to the front, and we move cat is happy to the end of the sentence. If and then stay where they are, we do not switch those words. We only switch the P and the Q. All right, go ahead and pause the video, see if you can do part B and find the conditional and the converse of that sentence. All right, so here it is. The conditional would be if a figure is a segment, then it is straight and has two endpoints. So our hypothesis being a figure is a segment, our conclusion being it is straight and has two endpoints. So then when we swap those, we're going to say if a figure is straight and has two endpoints, then the figure is a segment. So notice when we talk about biconditionals, we're talking about them both being P implies Q and Q implies P. Here. So we have our if P then Q, and we have our if Q then P. So we're going to use the conditional and the converse when we're doing this. And we know this statement is a biconditional because of a very important wording, and that's this if and only if statement. If and only if means that if one of them is true, then they both have to be true. So it's going to imply that all four of these statements are either true or all four are false. Notice here, if we look at this, lots of times geometric definitions are going to be biconditional statements, or at least conditional statements, right? So the definition of a segment is that it's straight and has two endpoints. So we can write that, and then the reverse is true, right? If we have a figure that's straight and has two endpoints, then it has to be a segment as well. So our biconditional statements use that terminology if and only if when describing that the conditional and the converse are both going to be the same truth value. So for question number 2, we're going to take the conditional, we're going to take the converse, and we're going to write it as a biconditional. So remember that phrasing that is super important to remember. Go ahead and look back in the video. I squared it or boxed it in green as we write these statements. The first thing we need to do is we need to find our hypothesis and our conclusion, find our P and Q. So if two angles share a side, remember if is not part of it, then they are adjacent. So we have our P and our Q, and note that they should swap in the converse. Okay, they share a side. Yes, that's swapped. And two angles are adjacent. Yeah, that's swapped too. That's cool. So now we can write our biconditional statement. So it's going to be our P, two angles share a side. And then this is when we're going to write the phrasing that makes it a biconditional. And that's the phrasing if and only if. And then we just write our conclusion. Right? They are adjacent. Okay, so the way we're going to write this statement is it's pretty plain and simple. We have our P, if and only if, and then our Q that follows. So there's not going to be any if at the start of the sentence. There's not going to be any then anywhere in the sentence. It's literally just going to be our P, if and only if, Q. Go ahead, pause the video, and see if you can write the biconditional for part B. All right, and here's your fun fact of the day. Something I found out recently, obviously with COVID, is that normal body temp is not 98.6 degrees anymore. For most of us, it's about a degree lower than that. And some research says that about 75% of people have lower body temp than 98.6. So if you're more about high 97s, low 98s, that's actually more normal. But anyways, back to your biconditional statements. Let's move on to number 3. All right, so here we talk about the truth values of these. A biconditional is true only if both the conditional and the converse are true. If the biconditional is false, we want to give a counterexample. So we need both the conditional and the converse to be true. So if x equals 1, then x is greater than 0. Is that a true or false statement? All right, so if x is equal to 1, then 1 is greater than 0. Yeah, that's very much a true statement. All right, let's look at the converse. If x is greater than 0, okay, so go ahead and pick your favorite number. Let's say 1. Cool. Then x equals 1. Oh, cool, that checked out. But is there another way to make the converse false? Can we pick a different number besides 1? Sure, let's pick 10, right? 10 is greater than 0. That checks out. But then is 10 equal to 1? No. So this one's going to be false. And because you didn't write true for both of these, the biconditional is automatically going to be false. And we need a counterexample, and we're going to say when x equals 10. Right? Because then it makes part of it true, but part of it also false. All right, part B. Go ahead and try this one on your own. See if you can figure out if this is going to be a true or false biconditional. Go ahead, pause the video. All right, so here we go. So our first conditional statement, if it is 3:30 a.m., then it is night. I would say this is true. Some of you might be able to say, well, if it's 3:30 a.m. here, it's nighttime. But when it's 3:30 here, then someplace else, it's daytime, right? But that's not 3:30 a.m. there, so that one's a little bit questionable, but I'd say mostly true. And then we get to the converse, though, is where the first part doesn't even actually make a difference. So if it's night, then it's 3:30 a.m. Well, that's false, right? Because it can be night, and it could be lots of different times other than 3:30. So this is going to be false, which makes the biconditional false as well. So that first one doesn't actually even matter, because one of them is false, we know it's false, right? So our counterexample was it can be night, but it could be 2 a.m. as well. So it doesn't have to be 3:30 a.m. All right, and let's see if we can figure this one out. So our conditional, we'll see if that's true or false, and then we'll look at the converse, and then that will tell us whether the biconditional is true or false. So I will graduate from high school. That's going to be our hypothesis. If and only if, right? That's our, tells us we have a biconditional statement. I earn a high school diploma. Tell if Maria's biconditional statement is true or false. So the conditional part there is going to say, I will graduate from high school. So if I graduate from high school, then I earn a high school diploma. That would be very true, right? If you graduate, you get a diploma. So let's look at the converse, right? If I earn a high school diploma, then I will graduate from high school. That is also a true statement. So then this biconditional is going to be true. Perfect. All right, moving on to question 4. Determine whether a true biconditional can be written from each conditional statement. If not, give a counterexample. So part A, if the lamp is unplugged, then the bulb does not shine. So if we look at our hypothesis here, the lamp is unplugged. Our conclusion, the bulb does not shine. So first of all, is that a true or false statement, right? If the lamp is unplugged, then the bulb does not shine. Yeah, absolutely. That definitely makes sense. If you haven't plugged in your lamp, the light's not going to work. So the converse here, or the conditional, is going to check out. So let's try the converse now. We're going to flip those, swap those. So if the bulb does not shine, then the lamp is unplugged. And so can we think of a reason why the bulb would not shine besides the lamp being unplugged? And yeah, we can, right? This one's going to be false. It could be that the bulb just doesn't work. It's out, right? Or it could be that the switch is down, even though the lamp is plugged in, if you got light switch for it or whatever the case is. So this is going to make the biconditional false as well. And our counter example would be anything that we said. So I'll say that the light switch is down. Or light switch is off. How about that? All right, in part B, the date can be the 29th if and only if it is not February. Go ahead and see if this is true or false. Kind of go through your tests. First of all, is the conditional true? Then is the converse true? And then that will tell you if the biconditional is true or not. All right, so here, the date can be the 29th if and only if it is not February. So we have, if the date is the 29th, then it is not February. And this is going to be false right off the bat, right? This conditional statement is false because it could be leap year. So the date could be the 29th, and it could be February. So I don't even need to worry about the converse. You can see I didn't even figure it out. But because the conditional is false, the biconditional is false, and I can say my example is leap year, where it could be the 29th and February at the same time. Okay. Once again, I did say a lot of definitions are written as biconditional statements. So go ahead, take these sentences and write them using the if and only if terminology. So a cube is a three-dimensional solid with 6 square faces. So we can take our hypothesis and say a cube, and then our conclusion is going to be the definition there. So, all right, so the first one would be a figure is a cube if and only if the figure is a three-dimensional solid with 6 square faces. Notice you can't just say a cube if and only if. You'd have to say, like, is a cube, just kind of to do that. All right, and then go ahead and do B, C, and D on your own. Go ahead and pause the video. When you come back, I'm just going to have answers to all 3 of them so you can see them. All right, so there's B for you. I am breathing. If and only if I am alive. All right, and the last 2 are here. Notice sometimes you do have to just add a couple extra words to make the sentence grammatically correct. That's cool. And if you ended up doing it a different way, say maybe you score 60% or higher, that's fine. Yeah, as long as you still have the pieces that are necessary in the right place. And then D, x plus 3 equals 10, if and only if x equals 7. All right, there is 2.4 for you. I know it's a lot of writing. Tomorrow, with 2.5, we're actually going to start proofs a little bit. So we'll get into a little bit more algebra with algebra proofs. So we'll move on to 2.5.